All right. Looks like everybody's back from lunch. I fortunately looked at my watch 10 minutes ago and was like, oh, we've all got to go. But really excited to start the afternoon session of day two. And it'll be started off with Dr. Christine Law talking about simultaneous brain spinal cord fMRI. Because I was so quick to get back here, I didn't write my normal introduction for Christine, but I'm going to wing it. And Dr. Christine Law is a research scientist in the Department of Anesthesiology, Perioperative, and Pain Medicine. She did her PhD with Dr. Gary Glover here at Stanford, then went to Oxford for a postdoc, and came back here for a second postdoc with the pain division, and has been a key player in helping us develop novel imaging technologies, and is a co-developer of this simultaneous brain spinal cord sequence that she'll be talking about. Also has experience in non-Cartesian acquisitions on samplings for MRI, acceleration methods, and advanced shimming techniques. Thank you, Christine. You're good.
I'm assuming people can hear me okay. Just go. All right. Simultaneous.
Can you hear Christine okay? Can you be louder?
I need to be louder. I didn't turn it on.
Oh.
Check the power first thing. I think I don't know whether to like this. So simultaneous brain and spinal cord acquisition. There are lots of challenges. So we talk about the challenges first. The first foremost challenge is visual inhomogeneity. Magnetic susceptibility difference between the spinal cord and the surrounding tissue make T2 star images suffer from signal loss and distortion. Geometric differences between the head, the neck, and the shoulder makes inhomogeneity worse. If you have a phantom, just agar phantom, uniform, but if it is shaped like a head and then the neck and the shoulder, like we have one in our lab, is just that itself is difficult to shim. So as you can imagine, putting a real person inside is not even more difficult. As you can see in these view maps, there are a few hundred hertz of resonance along the brain and the spinal cord. To address this visual inhomogeneity challenge, we use a dynamic per slide shimming method. The second challenge is cardiac-induced motion. Spinal cord moves in synchrony with cardiac cycle. But the motion is also dependent on the cord location. You can use cardiac gating to minimize the motion, but we are not talking about that here today. Instead, we'll use cardiac post-processing to reduce cardiac-induced motion. The third challenge is the small size of the cord. The largest cross section is only about a centimeter wide. This requires high resolution to resolve fine structure, but high resolution also means longer readout and a longer echo time. And these factors contribute to signal loss and distortion, and we will deal with this challenge by using a reduced field of view acquisition. I'll discuss shimming here next. Our method uses one set of static second-order shim for both the brain and the spine, but a distinct set of delta F linear XYZ shim for each and every slice. We also use both axial and sagittal field maps to calculate the amount of resonance. Of resonance varies the most along the spinal cord, affecting delta F and linear Z shims. Axial field map can only provide a coarse resolution in the Z dimension. That is why we collect a high resolution sagittal field map. Sagittal field map is collected under breath hold, so it eliminates breathing artifacts. All the shimming details are published in this paper. I'm just going to give a snapshot here. The first step in shimming calculation is to compute the second order shims, delta F and linear XY shims using the axial field maps. The of resonance we want to compute can be approximated by multiplication between a spatial encoding matrix and the unknown shim amplitudes. The vector O of resonance values are obtained from the axial field maps. Vector S includes second order shims that covers both the brain and spine. The next three entries are the linear XY and delta F shims for the first slice, then the second slice, and so on. Matrix E consists of spatial coordinates of voxels we want to shim. And finally, shim amplitude S is computed by least square. And we also, it's not shown here in this formulation, but we also constrain the second order shim magnitude because in our scanner, we cannot put in more than 4 amperes. So far, we haven't calculated the linear Z shims yet because we need to use a sagittal field map with higher resolution in the Z dimension. For each slice, we plot the of resonance values around that slice. Here we use a plus and minus 4 centimeter window for plotting. We'll come back to that later. We then fit a quadratic curve to these values. The slope of the tangent is the linear Z shim we need to compensate. We also update the delta F shim using the of resonance values found here. And the entire shimming calculation is done via a MATLAB executable that we install on the scanner. The calculation is about 2 minutes, and I'll show you the shimming procedure tomorrow at the scanner. As I have just mentioned, we use a 8 centimeter windows to do this calculation for the Z shim value. The reason we use 8 centimeters is because it has been giving us good images. But what about slices that is not so, doesn't vary so uniformly? So recently we started using different length of the window, 4 centimeters, 2 centimeters, and half a centimeters. And I'll show that now. This is an example of using different window lengths in the Z dimension for quadratic fitting. If you use a length of 8 centimeter, these are the values you will include in your quadratic fit for this slice right here, the black one. The resulting slope is very different if you were to use, say, a 4 centimeter window or a half centimeter window as I shown here. This is another example. The magnetic field around the target slice, represented here by this dot, is not very smooth. So using an 8 centimeter windows for fitting will give you this slope. But if you only use a 2 centimeter window, around the target, you get a steeper slope. And what does it do to the images? Well, all these images are used 8 centimeter windows for fitting. They look good overall. This one is the one that we will pay attention to. We see that there's some signal loss. So if we use a 4 centimeter window, it looks a little bit better. Using a 2 centimeter window, you get most of the in-plane signal loss recovered. So our pipeline now is to collect different, use different window length to collect, run the calculation and collect a set of test images, and we pick and choose the best slides. All right, let's look at the pulse sequence. We have used our pulse sequence on the Premier and on the 750 scanner. Now on the Premier, we're using a custom-built 56-channel coil built by Julian's team. On the 750, we previously have used a 16-channel coil or even a 12-channel coil. Most of the images are shown here were used the 16-channel coil on the 750. These are the scanning parameters. We use a spectral spatial pulse for the brain and a reduced field of view 2DR pulse for smaller voxels in the cord. So this is the actual scan area, but on the G scanner, you can't change the extent of the slice location, so it will show you a much larger area, but it's actually just this part. We have used 4 millimeter or 5 millimeter slice thickness. And we keep the slice thickness the same for both the brain and the spinal cord. These are the pulse sequence diagrams, spectral spatial pulse for the brain, and EPI readout, graph of 2, reduced field of view RF pulse for the spinal cord, same EPI readout. These are images we collected from a healthy participant, going from the top to bottom, represent inferior part of the brain to the superior part. Same representation for the spinal cord. We play a bit around of the voxel size and look at the TSNR. As you all know, for spinal cord fMRI, TSNR is more precious than ever. At the same time, we want high spatial resolution, but these two things don't go together. So if we make a small change from 1.25 by 1.25 to 5 millimeter to 1 by 1 by 5, you do see you get more voxel to represent the spinal cord. These two set of images, I would say they look both decent. What about the TSNR? These are the TSNR maps from the images that are shown. I kept the color scale maximum at 20. So the yellow color represents TSNR of 20 or more. As you can see, going from 1.25 to 1 in plane resolution, as you can expect, there's drop in TSNR. And if you do the calculation, you will find that it actually dropped by about 30%. And if you want a resolution of 1 by 1 by 3, you further drop another 30% in TSNR. So in that case, you will need to increase your TR to get enough more slices to cover the region you want to cover. And you may need to scan longer to get enough TSNR. So it's important to run pilots to make sure you have enough power to see what you want to see. We also implement a multi-echo version of the spinal cord brain sequence. Here I'm just showing the spinal cord part. In order to get a decent TR, I heavily accelerate the readout. So to get this kind of TR for the 3 echoes. These are echo 1, 2, and 3. And these are the images. So even with heavily accelerated readout, the multi-echo images looks okay, acceptable. This is another example of direct comparison of single echo to multi-echo images. Single echo use TE of 30. Most spinal cord images looks okay. A few of them are not optimal. This one. And this is a single volume. This is a second volume that I took. It's not average. This first echo from the multi-echo acquisition has a TE of 13.6. A lot of signal dropout around the frontal regions are not there, and the spinal cord images looks beautiful. The second echo has a TE of 30.9, similar to the 30 in the single echo. The second echo should be the closest to the single echo acquisition, but you can see that they're not identical, especially in the frontal region. The reason is because in multi-echo, I also use partial Fourier to accelerate, and that partial Fourier was not used in single echo. And the spinal cord images look similar to the single echo images. For the third echo, T is 52.1. More signal dropped out in the brain and the spinal cord. Okay, so now we talk about some applications and results. The first application is about thermal intensity encoding. You can find the preprint here on bioRxiv. The design went like this. We have a few seconds of anticipation where participants will see the word ready on the screen, meaning the thermal pain will be coming up. During the thermal pain, participants see a plus sign. The duration was 12 seconds, which includes 1 or 2 seconds of ramping up from 32 Celsius and 1 or 2 seconds ramping down. After each thermal pain, there was a 3.5 rating period where participants will use a button box to record their pain intensity from the heat trial. It went from no pain to the worst pain imaginable. They rated using the right hand. This is the same hand as the thermal pain was applied. And then there was a baseline of 9 seconds between trials. Total of 24 trials. The heat can be these 3 temperatures, pseudo-randomized. Even with this change of 1 to 2 Celsius, we can see a significant increase in pain intensity that they perceived. 46 was about close to 4, 47 was less than 6, and then 48 was about a 7. All right, what about activation? The thermal was placed on the right forearm, so that corresponds to dermatome spinal cord segment level C6. Brain activation and deactivation from 46, 47, and 48 are shown in these 3 columns. And brain regions that activate and deactivate linearly with the 3 temperatures are shown in this column on the right. These are classic pain-related activation patterns. For spinal cord, activation from each temperatures are shown here. They are noisier and more difficult to digest. But if you look at the activation corresponds to the linear increase of temperature, you can see the activation is mostly on the right side of the cord as we expected. To look at brain and spinal cord functional connectivity, we use the right dorsal quadrant as seed. Correlation from this seed to brain was carried out after signal from thermal pain was removed from the brain. Brain regions having significant correlation with the right dorsal quadrant are shown here on the right. The bottom figure shows correlation between individual average pain ratings and individual functional connectivity strength. Parameter estimate of these regions are shown, and the average pain rating from each participant are shown in these scatter plots. So there's a nice linear relationship between activation and deactivation and pain ratings. These works were done by Dario and Merv. Now, the second application I show here is transcranial electrical nerve stimulation, or TENS. Here we want to target the median nerve on the right hand. So one electrode was placed here and another one on the back side of the hand. We use a simple on and off design for 7.5 minutes. The result that I'm showing here was from a single scan done almost 6 years ago. Brain activation include left motor, left insular, thalamus, and the right cerebellum. Spinal cord activation spread out across segment C6 to C8, mostly on the right side, but there's some activation on the left side in C7 as well. But it's a single subject, so we haven't done TENS too much yet. Let's see. All right, the next application I want to talk about is mechanical pressure pain hemodynamics. And the motivation came from 2 recent papers. This is the first paper that motivated us. Is from Christian Buchow's group. They apply thermal pain and pressure pain to their participants. And they find that activation time course for thermal pains was more prolonged and often peak as stimulus went on, while pressure pain was more phasic. This figure shows activation time course in 4 brain regions. And the blue represent pressure pain and orange is thermal pain. And the 3 plots represent pain level of 30, 50, and 70 out of 100. And the second paper that motivated us is this preprint from the Max Planck's group. They look at thermal pain in spinal cord at 70. They analyze the data using a conventional boxcar convolved with HRF to look at tonic thermal pain response. And again, modeling the early part of the stimuli to find the phasic response. And they find that tonic and phasic responses took place at different layers in the spinal cord dorsal horn. Those 2 papers remind me of our mechanical pressure pain pilot data using simultaneous brain and spinal cord acquisition. The research question I want to answer is, what is the temporal dynamics of mechanical pressure pain in the brain and in the spinal cord? The design went like this. I have a few seconds of anticipation where they see the word ready, meaning pressure pain will come on. Mechanical pressure pain was applied for 10 seconds. We used this custom-built MR-safe device made by Gary Glover here. After pressure pain, participants will rate their pain intensity and pain unpleasantness using a button box on their right hand. There was a 10 seconds baseline between trials and a total of 21 trials. First, I analyzed the data using conventional way we usually do, which is modeling each event by a boxcar convolving with a HRF. And I will refer this as a full HRF analysis method. To see temporal dynamics, I reran the analysis using modeling the anticipation period as before, but for pressure pain and rating, I modeled them using finite impulse response or FIR basis function. I used 8 unconvolved time point regressors, which we will call them bins. Each bin represents 2.5 seconds, which is same as our TR. My goal is to use enough bins to cover time that contain no activities from pressure pain and from rating. We can look at activation from each bin because these bins are not convolved with HRF. The analysis power is even less, but because they're not convolved with HRF, the activation represented by each bin will be coming from that time interval and that time interval alone. I'm showing here group result of 5 subjects. Bin 1, this is the bin 1 I call bin 1. It aligned with well, it starts at 2.5 seconds later after the pressure pain onset. We have to keep in mind that there's a few seconds of hemodynamic delay. So I expect this period will see some activation related to pressure pain, maybe just the beginning. And we indeed see activation in the primary, sensory, ACC, insular, and cerebellum. What is nice is that we see, because pressure was applied on the left thumb, sensory activation is seen in the right sensory and the left cerebellum. And spinal cord segment level C6 shows activation in the left dorsal horn. Pin 2 didn't have any activation in the brain or the spinal cord, which was kind of surprising. Pin 3 has no activation in the brain either, but there's some spinal cord activation in the contralateral horn and central dorsal region. We're not quite sure what that means. Could be downregulation of pain or could be noise. Pin 4 aligned with the start of rating. Within this pin, I would expect there could be some activation from the pressure pain, should there be any, but there were none. This pin also may capture activities from the beginning of the rating. And we indeed see some evidence showing ratings here, including the left motor, SMA, premotor, visual cortex, and spinal cord showed the right hemichord activation, and possibly because people are using the right hand to rate. If we look at the results from conventional full HRF analysis, we see the average activation from the entire 10 seconds pressure pain. Some important informations are lost. For example, the right sensory activation is much less, and the left dorsal spinal cord activation is not seen here. So from this data, we see that mechanical pressure pain produces mostly phasic onset responses with matched cortical dorsal horn engagement. But this important information is lost if we just use the conventional analysis. All right. So next, I'm not showing result. I'm just going to show you our setup. We also do condition pain modulation, and just want to remind everyone. So if condition pain modulation says if you have one pain, that pain may feel less if you have a second pain. So we use thermal pain for the what we call the primary the target, the test stimulus, and cold water as the condition stimulus. Cold water bath is kind of standard for condition pain modulation, but people usually don't do it in the scanner for obvious reasons. But we did. So the design goes like this. We have two buckets of water. One is cold, one is skin temperature. and we have some valves that is the opening and closing of the valves is controlled by E prime, and we have a bucket. We have a fearless volunteer right here. Put their foot inside. So we have a tube going in, fill up the water, and then there's another valve controlling the outflow of the water going in this bucket here. So what we wanted to do was and there's a thermal pane on the right hand that you don't see the thermal here, but you see the button box. They also rate that pane. 5 minutes. Really? I okay. 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 So yeah, this is my second to last slide. So well, so what we want to do is we want to apply thermal pain on the right hand multiple times, during which we'll put cold water on their foot, and then we'll do it again with the 32 degrees water because we have to contrast. Now, but we don't want the cold water just to sit around and doing for like 4 or 5 minutes, because the water will get warmer and so on. So every once in a while, the valve will open and close, so we get a little fresh water in the bucket, in the foot bucket, and then we have to get some water out so that it doesn't overflow. Yeah, so the order of cold and normal water is randomized. Okay, so this is a movie showing just what we do. So first, this is a bucket of warm water. You see the water going down. This is during the water fill period, and the water now is going inside this bucket. You see that we're also connecting skin conductance and the heart rate. This is a monitor of the temperature. After water filling this up, they will rate the foot pain intensity. There should be none because it should be warm water. Now, so this is like the little changing water period that I'm talking about, so that we keep the temperature constant. So going out a little bit, filling up a bit. Now they see the word ready, so thermal pain is going up. This is that looks like a 47 or 48 Celsius for 13 seconds. Or 40. After each thermal pain, they will rate their arm pain intensity. And this cycle will go on for, I believe, 9 times. So a little water exchange, anticipation, thermal pain, and then rating. After 9 times of this, we'll ask them one more time what their foot pain is. And then now we drain the warm water out. And the cold water goes down. You see there's some ice there. And this is the temperature that we are measuring. This is, yeah. And we do the whole thing again. All right, so that's the setup. That would be setup. Yeah, I don't know. Yeah. All right. So this is all I have for my talk. So to summarize, I talk about the importance of shimming, how we did it, and I'll show you how I do it on the scanner tomorrow. We take a brief look at voxel size versus TSNR. Multi-echo acquisition is possible. We have some data we haven't fully analyzed them quite yet. And the nice thing about why we want to do this, because we can look at the cool connection between brain and spinal cord and see what our central nervous system is doing. And because I spent so much time making this figure, so I want to show it again. And thank you for all our collaborators. Yeah, questions?
Great job, Christine. Just a note, I had said that water conditioned pain modulation experiment was too hard. Nobody could possibly make it. But then Gary did it. And it's pretty awesome to be proven wrong. Awesome job. Open it up to in questions from the group. Anyone have any questions?
I guess I'll get started. Thank you very much. So I have a question on the dynamic shimming. I missed it, but the XYZ gradients, are they applied continuously, or are they blips?
They apply continuously.
Continuously, and it includes the RF pulse as well.
Yes.
Yes. Okay. And have you looked into navigator, correction for multi-echo, for example, whereas whether EPIs or GREs, simple GREs, like what group of Johanna Panistro has been doing?
Whether we have looked at navigator for multi-echo?
Yeah.
No.
To basically, correct for the phase offset due to breathing.
Breathing correction, all that. It's multi-echo single.
On EPI.
Sure.
Yeah. Right. I was thinking more like multi-echo GRE. Yeah. That's something we can discuss later.
No, I'm hoping the next thing we do that's close to multi-echo is EPPI. Oh.
Thank you, great talk. I wanted to just ask you if when analyzing this data, did you apply a mask to the spinal cord fMRI data?
Yes.
And the mask was just the cord itself?
In the analysis?
Mm-hmm.
Yeah, just the cord itself. Yeah.
Yeah, instead of white matter mask, gray matter mask. Included.
Thanks for the talk, Christine. I have a slightly off-topic question. Are there other ways of assessing pain besides the NRS? Like, maybe so, because I feel like the VAS or like the NRS where you score 0 to 10 is maybe very subjective, and also maybe over weeks can change. So I don't know if there's any slightly more objective measures of measuring pain.
Ken, you want to take it?
Yeah, I think we're limited in the subjectivity. Gold standard is the numerical rating scale, 0 to 10, 0 to 100. Usually 0 to 10. We also have, we didn't in this collect pain and pleasantness. We have collected that as well to try to get more at the affective aspect, emotional aspect, evaluation of the pain. But they tend to be really highly correlated, at least in these experimental acute pain paradigms.
And in this experiment, we also had, although the signal code is questionable, peripheral markers of pain, which I'm forgetting, the skin conductance. Yeah, so that would be a peripheral marker.
Did the subjects report any differences in the qualia of the percept when you're giving the stimuli?
Sorry,
In addition to the intensity, do they report differences in the qualia of the percept, like if it's burning or kind of tingling or others?
no.
We don't know.
We try to make the scan as short as possible.
And then the others, are you measuring the thermal temperature of the foot during the temperature changes? So like people have seen when they measure between different people, some people they're just do vascular, they'll actually renormalize at different rates. And I'm wondering if you actually were to compare that renormalization when it goes back to baseline with their actual activity in their cord, if you actually see differences or if the actual dynamics are similar, even though their temperature of the periphery is actually changing at a different rate.
From the skin conductance data?
Or if you, I don't know if you have thermal imaging or some way to actually directly measure the temperature of their peripheral body part.
Is the skin conductance at temperature? No, we don't measure people's skin temperature.
Try to do to make it more consistent is give some ample time. The water comes in, and then there's about half a minute before the first heat stimulus comes in. Yeah.
So I guess there's an assumption reporting on the offset. So then we've seen it with mice. If you do the cold on the offset, the time constant of returning will be different. That's something that's correlate with that activity. And I'm wondering if you see something similar in the humans.
Interesting.
Yeah, and additional questions.
Maybe I missed it, but how do you know the multi-echo? How do you use the multi-echo data for the analysis? How do you combine them?
What's the thing called? Banana, yeah. But you can just use it out of the box for the brain.
Okay.
For the spinal cord, you have to play around a little bit. The mass is obviously different. You probably use your own mass accounting.
I see. And did you compare the multi-echo fMRI versus a single echo one? For example, for a given task, which one gives you more activated voxels, higher detectability?
It's still in the work. We'll have some data, but some analysis result, but nothing. Not all of them is fully analyzed yet.
Yeah, so the multi-echo approach is to use multi-echo ICA denoising to be able to identify which components are bold and non-bold, and then remove the non-bold components. And there's the Tadana package that can do this. We have the data set so to be able to try to compare. Does the multi-echo imaging help us with denoising the spinal cord data? No. Any additional questions? Any online questions? No? All right. Maybe take a few minute break, and then we'll start the panel discussion at 2. Is that okay? Okay.